Hi everyone, warm welcome from my side. My name is Rohan Pandit. I am working as a product manager at ETAS, located in Stuttgart in Germany. I've been part of ETAS since June of 2018, so around 6 years, and I have been working in the automotive security industry for the last 6 years together with ETAS.
Yeah, thanks, Rohan. My name is Michael Eitzberger. I'm Senior Product Marketing Manager at Infineon. From my background, I'm engineering and management, Master of Engineer, and I have also a passion here to bridge always technology with business. I joined Infineon in 21 and have also more than 10 years automotive industry experience. Before I worked also at Bosch.
Hi everyone, my name is Laurent Heitz. I am cybersecurity system architect for our Oryx microcontroller. I'm working in the domain of automotive since about 20 years, and out of which about half of the time for cybersecurity.
Yeah, thanks, Laurent. And again, also very warm welcome from Infineon side. Thanks a lot for joining this webinar. From the structure, we will now start with an introduction into automotive cybersecurity trends. Then we will show you how we cover those trends with the Oryx TC4X family. And then Rohan from ETAS will take over and present also how the software part works together with our hardware. So to give you an overview, and then we will also go more into the details on the next pages, we see currently three main trends which are highly influencing the automotive cybersecurity. The first one is the ISO 21434. The second, the new E architecture in general. And then last but not least, the post-quantum cryptography. And all those three trends have a major impact on the automotive cybersecurity requirements and also leading to higher and increased security requirements for the automotive microcontrollers. For example, with the ISO 21434, we see a need for type approval from the OEMs for upcoming car models. Also from the new E architecture, we see an increased security demand, increased security use cases, and also higher performance requirements. And with the post-quantum cryptography, we see that current crypto primitives will deprecate and also have a limited security in the future. And overall, all those trends are leading to increasing and leading to higher microcontroller performance demand. Now, let's take a deeper look into the ISO 21434, which becomes really a main condition, precondition for the complete automotive supply chain. And from background, so the UNECE regulations, which are concerning the approval of vehicles with regards to cybersecurity and cybersecurity management system since 2022, they are demanding now so-called type approval certificates for the new car models. So the OEMs need this type approval certificate. And this means for the complete supply chain, so tier ones, tier twos, and also the ECU and MCU suppliers, that they have to be compliant to the respective standards, such as the ISO 21434. The ISO 21434 contains 5 main work packages. The first one is cybersecurity management, continuous cybersecurity activities, such as monitoring, risk assessment, vulnerability analysis. Also risk assessment methods, for example, threat identification, TADA, and also last but not least, concept phase implementation, such as cybersecurity goals. Also contains the product development phase, integration, verification, and last but not least, also the post-development phase, means a cybersecurity incident response process. And all in all, it becomes really a clear main condition, precondition for the supply chain. We see this also in all the RFQs which we receive in the meantime. The second trend, as already mentioned, the new E architecture, but how is it influencing the cybersecurity cluster? So in the new E architecture, we see currently 3 main layers. This means the first one is the central car computer. Then we see a so-called middle layer, zone and domain structure based. And then last but not least, the endpoint ECUs, such as braking, steering, or propulsion applications. And within this new E-architecture, we see more communication coming. We see also Ethernet coming. And this means that we need a minimized latency and a maximized throughput for this in-vehicle network communication between the zones, between the central car computer, and between the endpoint nodes. And this means we have also to get ready for Ethernet. For sure, if we also talk about the car of the future, we have to enable software over the air use cases, which require secured and safe distribution of software updates from the cloud or within the in-vehicle network. And we see also, so the first topic is that we see more communication in the car. And the third topic is that we see also an increased need for security for those messages. This means we see more than 50% of those messages authenticated, and we see an encryption of between 15 and 20% of all in-vehicle network messages. Last but not least, we see also an increasing number of security use cases to be covered. This means, for example, secured updates, connection to external service providers. For example, if we talk about charging stations, we see also the needs for device attestation, runtime manipulation detection, feature activation. So also if you want to activate more features, also as Tesla, for example, is already offering, then you need really more security use cases to be covered. And this means also that an enhanced security cluster is needed. Last but not least, quantum cryptography or post-quantum cryptography has a major impact on the automotive supply chain, on the automotive cybersecurity, and must be considered already now. So why is this the case? So we expect an availability between 2030 and 2035. So quantum computers with usage for crypto analysis are expected in this time frame to be ready. And for sure, this is also very relevant for automotive life cycles and next SOPs. So for example, if we talk about an SOP timeframe 27, 28, which we are currently working on in the development phase, then we are directly in this timeframe. The post-quantum cryptography has also a strong influence on the key and encryption standards. This means, on the one hand side, asymmetric ciphers getting insecure, and the major symmetric ciphers, such as AES 128, will have a reduced security. What we currently, or what the industry is currently considering as quantum resistant are AES 256, SHA 512, and SHA 3 512. The NIST, as a standardization gremium, is already working on the algorithms to cover the post-quantum cryptography, and the first batch of algorithms should be finalized by end of 24. We have then also a slide showing what's currently in the final phase, and we will also show how we already run those algorithms on a TC4X. But all in all, it has an impact already now. It has a strong influence on the way we are working, and it has to be considered from the industry right now. So those were the three main trends we see, and now we want to give you an insight how the Aurix TC4X family is covering those trends and how we are setting really new standards in automotive cybersecurity. But before we go into the details of the cybersecurity cluster, we also want to give you an outlook on the overall structure of the TC4X family. First of all, we implemented a higher performance compared to the TC3X family. This means a new tri-core family 1.8 with up to 500 megahertz performance. We also implemented a coprocessor unit, the so-called PPU, parallel processing unit, which contains a private scalar core and a vector unit, and is perfectly fit, for example, for neural networks. We also implemented a new converter subsystem with integrated and programmable DSPs, data routing engines for CAN Ethernet communication, improved timers, and furthermore. So really a higher performance as we have seen before, and also a benchmark in the industry here. Then from safety and security side, for sure, we are meeting the ISO 26262 SLD safety standards. We even enhanced the TC3 system here, but we also kept what was already very good established there. From security side, we brought really a new security cluster in. So first of all, with the CSRM, the cybersecurity real-time module, which is a high-performance security module with private CPU, with private memories and crypto accelerators. And in addition, also the CSS, cybersecurity satellite for distributed crypto and hash engines. This we will also show you for sure more into details. And we are also certified according to the ISO 21434 security standard. Then also very important for the new E-architecture, especially for domain zone controllers, we put a lot of emphasis in the freedom from interference part. So we implemented a hardware isolation at core and peripheral level. This means the Tri-Core 1.8 has up to 8 virtual machines per core and a hypervisor. We implemented ultra-fast context switching and furthermore. And also from connectivity perspective, we really brought in a lot of new innovations like 5 gigabit Ethernet, including bridge, also accelerated MAC-SEC support, 100 megabit Ethernet, also supporting the new 10BASE-T1S standard, PCI Express, CAN-FD, and also CAN-XL. So overall, the RX TC4X family defines the next controller standard for a safe and secure ECU with really strong networking capabilities. Then coming back to the 3 trends and how we cover it with the TC3, I don't want to repeat all the topics, but if we remember right from ISO 21434 perspective, we already said that the OEMs need this type approval. This means at the end that the supply chain has to be compliant to the ISO 21434, and the tier 1 or T2 as MCU integrator has to check and prove this compliance. And we can really help our customers here because as we are already certificated according to the ISO 21434, the customer has no need to check this ISO 21434 compliance for our products as we already did it. So customer can really save time and resources for that. Then from the ISO, from the new E-architecture topic, as already said, we see more requirements based on platform on communication security use cases. We see also the need for increased performance, and this we solve with the CSRM and the CSS. So we solve the performance bottlenecks which we currently see in classic HSM with that approach. And last but not least, post-quantum cryptography, as mentioned. So public keys will become unsecure and symmetric keys will have a limited security. And this we solve with the TC4X with a hardware acceleration, which we are offering, such as multiple AES 256, SHA-3, and SHAKE. And we also support post-quantum algorithms, which we show you then also in a minute. Overall, the TC4X will be compliant to ISO 21434. We solve existing performance bottlenecks, and we are post-quantum ready. Then we also want to show you the certification we received from TÜV Nord. So the certification includes all the topics which explained before. So for example, cybersecurity management, continuous cyber security activities, risk assessment methods, and so on. And with the certification, we could prove our position as trusted partner in automotive cybersecurity by an external party. Now, let's go into the details of our security cluster. So, as already mentioned, we implemented 2 main clusters, the CSS, so cybersecurity satellite for parallel computation. This means it enables a parallelization of hardware accelerators to avoid performance bottlenecks by increasing throughput and by minimizing latencies. And multiple channels can be used by the application C. So we have here multiple channels which can be used. We also implemented an avoidance of systematic faults to ensure the customer system availability. And secondly, we implemented the CSRM, Cybersecurity Real-Time Module. And here we implemented a tri-core as a core. Before we had in the HSM of the TC3 an ARM M3, and this provides up to 15 times more performance. We also implemented here an own private non-volatile memory. This means with the private non-volatile memory, we support individual security software updates independently of the application core. Overall, cybersecurity cluster of the TC4X increases throughput by the parallel computation, and we're also supporting upcoming security standards. We also prepared some benchmark figures, which we show you then in a minute. Then, as already mentioned, post-quantum cryptography, there are currently a few algorithms which reached the round 4 in the NIST process. This is, for example, for key encapsulation mechanisms, a lattice-based algorithm which is called Kyber. From signature schemes, currently lattice-based is selected dilithium and falcium, symmetric and hash strings. And all those 4 algorithms are already implemented successfully on an RxTC4 for demo purpose. So this is non-productive, but we already implemented that one. There are also two algorithms which reached the final round, but are currently not yet selected. So as already mentioned, we add significant performance compared to the HSM, and we could also prove that and can also prove that in benchmark figures. So here we prepared 4 benchmarks. The first one is cyber blockchaining, CBC. So here we see that the TC4X provides 16 times more throughput than a TC3. For CMAC, we can prove 7 times more throughput per channel. And as said, we have also multiple channels. For Galois and counter mode, 21 times more throughput. And last but not least, we also compared public key crypto RSA 2048 on a TC3, which is currently standard for public key. And we compared it to post-quantum crypto dilithium 2 on a TC4. And here we could see that we have an 8 times faster signing time. So with that, we can prove also with public key, we are able to be even faster than on RSA on a TC3. Overall, as already mentioned, the TC4X really adds significant performance. And as already mentioned, but I want also to emphasize this one more, all those simulations have been done on one AES channels of the CSS, and we have several. So this means we can even multiply those performance figures. With that, I end my presentation part and hand over to Rohan, and then we're looking forward to your questions at the end.
All right. Thank you, Michael. So Michael has explained more about how the hardware on the TC4X has been evolved owing to the new e-architecture trends and the SDV impact. And this also then has an impact on the evolution of CyberHSM as well. So let's have a look how the HSM firmware also has evolved owing to the changes in the industry. So if we look at the evolution of e-architecture, you see that a lot of functionality is being moved from hardware to software, which means a higher software complexity, which has to be managed on the firmware side. There is a significant increase in the network communication requirements owing to the different new channels which have been introduced. There's a requirement for dynamic firmware updates because you see a lot of multi-tier collaboration happening in ECU development. Of course, there is requirements from functional safety point of view, which have been introduced because of the new complex EE architecture. There's a requirement for next level security hardening owing to the wider attack surface area. And this eventually leads also to the evolution of the automotive microcontrollers. And with this, the new automotive microcontrollers are adding more memory resources, much more improved performance with the help of security clusters that Michael mentioned, like CSS. And this is significantly improving the overall performance on the system. In addition, there are also enhanced symmetric as well as asymmetric crypto accelerators, which are now available on the new devices. And last but not the least, the support for virtual environments. This gives the user an option to create several new virtual instances on the host side, which can be used to perform different functionalities independent of each other. And all of these eventually lead to a need for a new security firmware, which is why we have introduced Scrypt CycleHSM 3.x. This is the new generation of HSM firmware, which is targeting to address the needs of the new EE architecture. So we see that there are a lot of new security challenges which are arising because of the introduction of the new EE architecture. And we can now have a look at a few of the security challenges and how we resolve them using the combination of Infineon hardware and ETAS software. So the first challenge that we have is with respect to SecurC bandwidth challenge. This arises because the current generation of microcontrollers have a performance bottleneck owing to the bridge interface between the host and the HSM. And here, this has been addressed now with the addition of the crypto accelerator or the CSS on the TC4X. So this significantly reduces the route that the SecurC message has to traverse. Instead of passing through all the different layers on the crypto stack, then through the bridge, and then to the HSM firmware, and finally to the hardware accelerator. Now you can see in the new generation of microcontrollers, the host can directly place jobs towards the crypto accelerator. Of course, we also have to ensure security, which is why the HSM firmware is still responsible for the key management functionality to ensure security so that the keys are verified and made available to the CSS so that the host can place SecurC messages towards the CSS. In addition, with the HSM 3.x, we provide new APIs as well to ease the process of placing jobs and also to initialize the CSS and load the keys from the HSM into the CSS. Another important factor to note is that this is not just improving SecurC, but also the overall startup time as well using the CSS accelerator. Okay. Then let's dive into an important question that we always see in the industry. So there is a question about why the firmware cannot match the performance offered by the silicons. So for this, I will try to answer this question with the factors or the different aspects that the CycleHSM has to consider while also ensuring optimal performance. So the first one being feature complexity. CycleHSM supports multi-session handling, several functional safety use cases, which are implemented on HSM in order to realize the different requirements from the OEMs. And some amount of performance is being utilized here in order to realize these different features. The second aspect is with respect to memory resources. The memory resources on the HSM hardware itself are quite limited, which is why we have to manage the wide range of features within the restricted memory available, which also leads to performance impact. The third most important aspect is with respect to security checks. HSM is a ISO 21434 certified solution, and we follow security by design principles in order to achieve the highest level of cybersecurity standards. And this takes up around 30% of the performance utilization here. But this is something which is important for Cycad HSM as the security trust anchor. Last but not the least is the platform approach that we have with Cycad HSM. We want to support all the major automotive silicons with the same standardized APIs and also a wide range of feature set. And in order to achieve all of this, we also have to have good level of hardware abstraction, which leads to also some sort of performance utilization. So while managing all these different aspects, we still try to optimize the timing performance, which is why you see a difference between the performance numbers on the HSM firmware and the ones provided from the silicon. Okay, let's look now at the next challenge that we have, which is about security hardening. So with the introduction of support for virtual machines and virtual instances, this also means that you need a better security hardening system in place. And this is achieved by having an efficient access management system in place. And if you see in this picture here, there are multiple virtual machines which are performing different functionalities. And depending on the use case, the user can define a virtual machine 1 as, say, for example, a functional safety relevant virtual machine. And based on this, also configure the resources available to it in accordance to the use cases as well. This means that you can have a granular level of access management done both in terms of functionality as well as resources which are made available to this virtual machine. Second aspect is regarding the ability to independently update the different virtual machines. So in a scenario where virtual machine 2 is attacked and not verified anymore, we still have to ensure system uptime without affecting the requests which are coming in, and we have to reject the request from the virtual machine 2 which is not verified anymore. And this can be achieved using HSM 3 firmware. So in general, we can achieve a lot of use cases by making use of HSM 3 firmware, which is combined with the hardware capability on the TC4X to achieve the best security hardening system. Then moving forward, the big challenge that we see today is with respect to post-quantum cryptography. Quantum computers will become a real security threat in the next 10 years or so. And this is because post-quantum computers will be able to lower the security of AES by a factor of 2. So for example, a AES 128-bit key is as secure as a 64-bit key. It will be very easy to break into asymmetric crypto of today, such as ECC and RSA, and which is why there is a dire need to have new crypto algorithms which are post-quantum resistant and are available to the vehicles before the attack comes into place. And this is the reason we see that major OEMs are also including PQC security requirements already in their security specifications. And this is done in order to have security in place for a long-term solution. NIST has already selected some crypto algorithms, and these are being also then further refined and updated as we speak. So how do we manage these challenges posed by post-quantum cryptography? So in order to do this, ETAS has a wide range of portfolio solutions. So the first one being with consulting. So we have a team of professional security services which are offering consulting services on how you can build your system to be PQC resistant. One more important aspect to note is that ETAS is participating in the Flocky project, which is a government-funded research project where we aim to have a post-quantum resistant public key infrastructure in place. And this is something which is important to have a system which is resistant against post-quantum attacks, and it's a long-term solution which can be offered on the vehicles. In terms of software solution, we have already implemented some of the selected NIST algorithms, such as Dilithium, which is a signature algorithm, the Kyber, which is a key exchange algorithm, and of course, we also plan to implement Sphinx Plus, which is a hash-based signature algorithm, and this is planned on our roadmap. The next step is to optimize this further using the hardware accelerators available on the TC4X, such as the AES-256 and SHA-2 and SHA-3. So the idea is to optimize the software implementation using the hardware accelerators available on the TC4X to achieve better performance as well as to manage the resource consumption of the post-quantum algorithms. So now let's also look at the HSM compliance as well. So Cycle HSM is a TÜV certified solution according to ISO 21434, and this is both for the product as well as the process. So we ensure that we are compliant with ISO 21434 to the highest level, which is level 4, right from the initial concept phase until the product is in field as well. So this is something quite important also going forward for a lot of OEMs. Now, in the next section, we will look at the collaboration between ETAS and Infineon and how we try to develop the best solutions. So ETAS and Infineon are working closely together, and this is starting already in the concept and design phase. So what we do together is collect all the trends and requirements from the OEMs and from the automotive market to use this as an input for our designs and concepts. Of course, one more key aspect to consider is with respect to standards and regulations. So here we are talking about UNECE requirements, ISO 21434, and the CSMS Cybersecurity Management System requirements as well. So this is used as an input for early samples development. And these initial hardware samples are then provided from Infineon to ETAS to be tested initially with early ETAS software, which is then used to test the hardware from Infineon. And this is used to provide feedback to be incorporated into the final series version provided by Infineon. Finally, we qualify this final hardware solution with the final ETA software so that it can be provided to the customers, which is fully automotive qualified according to the latest standards and regulations. But this doesn't stop here. We also keep continuously monitoring what is happening in field, what are the learnings and findings based on the customer feedback and from the industry itself. And this is used as an input for generation of the next solutions that are being planned already today. So this regular monitoring and update of both the hardware and software ensures a long-term security and performance of the system. So now looking at all that we have seen in today's webinar, let's try to summarize why Scrypt Cycle HSM and Infineon automotive microcontrollers are a perfect match for each other. So first aspect is the cybersecurity satellite support. With the introduction of cybersecurity satellite, Cycle HSM is able to provide an improved performance by a factor between 5 to 15, not just for SecOC, but also for Secure Boot. And this is achieved based on the introduction of CSS, and this is optimized according to the HSM security requirements as well. Second factor we have to consider is the support for hardware virtualization features. And Cycle HSM offers the ability to integrate into any hypervisor environment. This includes also Type 3 virtual environments. Type 3 hypervisor implies that it resides on the physical hardware itself. With respect to cryptographic functions, Cycle HSM is supporting a wide range of cryptographic functions, and these are being hardware accelerated using the accelerators available on the TC4X. The ones which are not available or supported by the hardware engine are then optimized by implementing it on our software library. With respect to OEM use cases, we have the most wide range of features supported on our solution, which are then able to realize the requirements of all the leading OEMs. And this includes also the support for virtualization feature, which is becoming more and more relevant as we speak. Of course, HSM is a easy to use and easy to integrate solution, which can be integrated into the low levels drivers available from the silicons, which can be then fully qualified and integrated into the systems. In addition, we also offer an easy to integrate solution with any ETAS or other flash bootloader vendor according to our CSI API interface, and also into any AUTOSAR and non-AUTOSAR environment as well. And for this, we offer a configurable crypto driver, which can be made available on request as well. So in summary, we try to optimize the Scrypt HSM firmware by leveraging the capabilities of the TC4X hardware. All right, with that, we come to the end of today's presentation. Thank you very much. Have a nice day.
Thank you. Bye.